In section 7.2, we're talking about similar polygons. Our objective is going to be to identify and apply similar polygons. Okay, we'll look at the geometric idea of similarity here, and then use that to approach a few different types of real-world problems towards the end of the lesson. Okay, here we go with that. Okay, when we say similar figures, we're talking about two figures that have the same shape, but not necessarily the same size. Okay, so when you hear similarity, you should be thinking scale model, scale diagram. Similar polygons, then, to have the same shape but not the same size, are going to have corresponding angles that are congruent and then corresponding sides that are proportional to each other. Okay, so for example, we have a set of two similar polygons here, same shape, not the same size. We'd write that as ABCD is similar to, that's our similar to symbol, the squiggly from on top of the congruent symbol, GHIJ. Now again, when we say they're similar to each other, that means each set of corresponding angles are congruent. So A is congruent to G, B and H will be congruent, C and I will be congruent, D and J will be congruent. And then the corresponding sides are similar, meaning that if I looked at the ratio of AB over GH, the corresponding sides, that'd be this ratio here, it's going to be equal to the ratio of BC over HI, or any other ratio made up of the corresponding sides. Now, when we write a bunch of ratios more than 2 equal to each other, we're going to call that extended proportion. Again, that's when 3 or more ratios are equal. And when we're talking about our congruent polygons, we're going to say the scale factor is the ratio of the corresponding linear measurements. Okay, so the scale factor is the ratio that we're plugging in to that proportion. All right, our first question is just going to look to check and see if we understand what's going on with similarity. Okay, it says that triangle MNP is similar to triangle SRT. In A, we want to know what are the pairs of congruent angles. Okay, so again, in similar polygons, corresponding angles are congruent to each other. So for example, if I look at angle N and angle R, it looks like they're corresponding. I could say that angle N is congruent to angle R. Same thing, M and S look like the bigger angles of these two similar triangles. So we could say angle M is congruent to angle S. And then we have the last set, but notice I don't actually even need to use the picture for this. Just like with the congruent statement, the similarity statement is going to match up corresponding parts. So P and T are both the last letters in my similarity statements. Therefore, I know that angle P is congruent to angle T without even looking at the picture here. Okay, in the same way, we can match up corresponding sides. B asks, what are the extended proportions for the ratios of corresponding sides? So let's get this stuff out of the way here quick. And so what are the extended proportions of the ratios of corresponding sides? We can start off with a set of corresponding sides. So for example, NM and RS. We can use that to make a ratio. This would also be my scale factor if I had some numbers. And we can set that equal to the ratios of the other sets of corresponding sides. So for example, MP and ST. Notice as I did that, I'm always keeping my smaller triangle on top, bigger one on bottom. I could flip it upside down, but once I make a choice to start, we'll finish with that. Okay, and then we could do the same thing with the last set of sides. Again, we could look at NP and RT. And with that similarity statement, we could do that without the picture even. We could just use the statement up top here. Okay, so when we say that two triangles are similar to each other, we know that all corresponding angles are congruent, and then we can set up a proportion with the corresponding linear measurements, the corresponding sides. In problem 2, we're going to determine if two polygons are similar. Part A asks, are the polygons similar? And we have triangle ABC and FED. Well, two things we need to check for that. First thing is the angles. And it looks like those match up. We have F and A are congruent. we have angle E and B are congruent. Those are marked for us. And then last thing, anytime we have two triangles with two angles congruent, we know that third angle will be congruent as well. That's our third angle theorem. So we could say that angle D is congruent to angle C. All right, so the angles work. Corresponding angles are congruent. The other part is we need to check and see if the corresponding sides are proportional. Here's how we'll do that. I'm going to look at DF over its corresponding side, CA. Now DF over CA is going to be equal to 16 over 8, which equals 2. Now what we need to do then is check the other sets of corresponding sides. So for example, FE over AB and check and see that we get the same scale factor, the same 2 here. Well, FE is 30. AB is 15, which equals 2 as well. So that works. And then we'll do the same thing with DE and CB, the last set of corresponding sides. DE over CB is going to be equal to 34 divided by 17, which equals 2 as well. Okay, so since we have the same scale factor, the same reduced ratio between all sets of corresponding sides, I'm going to say the sides check out as well. So answer to this problem then is yes, they are similar. Okay, problem 2b is the same idea. Two polygons, you want to see if they're similar or not. Why don't you take a second and pause the video, give 2b a shot, and then hit play to check your answers. All right, next thing we're going to do in problem 3 is use similarity to solve for different parts of similar polygons. So here we have ABCD is similar to EFGD. Okay, so it looks like our larger polygon is similar to the smaller one. We want to know what is the value of x. Now, trick for this, what we can do is set up a proportion. I have the side length with an x, and I know its corresponding side length. So I can set up x over 7.5. And then we can set that equal to another side on the same polygon that we know is this side length of 6. So we can say equals 6 over, since we know this 9, the longer side length, we can use that. Oops, 9. And with that, we can set up a proportion. We can solve our proportion, and the solution to that will give us our x value. Okay, cross multiply. 9 times x will give us 9x is equal to our other cross product, 7.5 times 6, which is 45. Okay, cross multiply and divide. Divide both sides of the equation by 9. And we end up with x is equal to 5. Okay, so again, if we know the corresponding measurement that matches up with what we're looking for, and we know a pair of corresponding measurements on the two similar polygons, we can use those to solve for that measurement we're missing. Part B is the same idea. Why don't you pause the video, take a minute to work that one out, and then hit play to check your answer. Okay, next thing we're going to do is take a look at how we can use similarity in the real world. Okay, problem 4, using a scaled diagram. A says the diagram shows a scale drawing of the Golden Gate Bridge in San Francisco. The distance between the two towers is the main span. What is the actual length of the main span of the bridge? Okay, here we're given the scale. And I actually have a ruler here to set up to figure out, how far the length is on the diagram. When they're talking about the main span, I believe they're talking about distance from kind of tower to tower here. So we can measure that. Let's see, it looks like I have 6.5, okay, for my distance in the scale drawing. So I can set up then is 6.5 over x, the distance of the actual bridge, is going to be equal to then our scale, where we have in the scale 1 centimeter is equal to 200 meters in the actual. Now, when we're setting up a proportion, we don't need to worry about conversions. All I need to do is cross multiply and divide, and the conversions will kind of be taken care of themselves. So taking my cross multiples, we'll have 1 times x is just an x, is equal to 200 times 6.5 is going to give me a 1,300. Okay, so the actual length of the main span is 1,300 meters. Okay, why don't you take a minute, give part B a shot, and check the answer. All right, problem 5, we have one more example of how we can use similarity. A says Mr. Bailey wants to take a 7-inch high by 5-inch wide picture and blow it up with his projector. The space his projector can cover is 42 inches high by 56 inches wide. What is the largest picture Mr. Bailey can display with his projector? Now, our first instinct would be to say, well, the biggest we can make this picture is 42 inches high and 56 inches wide. Here's the issue we run into, though. When I take this picture and go to blow it up the full size, what happens? Well, it gets distorted. It gets too fat in this case. So what I need to do here actually is I'm going to say fix the aspect ratio. I need to figure out how big I can make this picture so that it blows up to scale. It's not changing the shape of the picture. Okay, so we saw here that the height of the picture is going to fit, but the width isn't. I can set up a proportion with that. We can say my original picture is 7 inches high over 5 inches wide, and that'll be equal to the height of the projector, 42, over, we're not sure what the width is going to be, we'll call that the x. Okay, cross multiply, we get 7x is equal to 210, and divide, we end up with x is equal to 30. Okay, again, x was the width, so we'd say the biggest picture we can end up with is 42 inches high, because that's what we fit was the width, and 30 inches wide. Okay, now one more quick thing with this one. It was nice to have this kind of visual to actually make the adjustments there and see how things are going to fit. But let's say I wasn't sure if it was the height that's going to fit perfectly or the width. Okay, basically what you can do to determine is just guess and check. What I could have set up is 7 over 5 is equal to x, we don't know the height, over the width, 56. When I multiply that then, we end up with a 5x is equal to 392. Divide that by 5, we end up with x is equal to 78.4. Well, if the width was 56 inches, the height would have to be 78.4 inches. Here my projector only goes up to 42 inches. Okay, so I know that would be too high. And if this was the first ratio I had set up, or the first proportion I set up, I'd have to set up the other one to actually solve for the width. Okay, part B is the same idea. Why don't you take a minute, give that a shot, pause the video, and then press play to check your answer.